today we're focusing on ionization energies. Now, ionization, we can have cations or anions that are positive or negative, but when we talk about ionizing something, we're actually specifically referring to the removal of electrons. So we're taking them away, and we're talking about how much energy is required to do that. So for some atoms, that will be relatively easy. For others, it'll be a lot harder, depending on their configuration and what charge from the nucleus is sort of being felt, if you like, by the electrons that are being removed. And we're talking about valence electrons here. And when we talk about trends, we're looking for patterns, discontinuities, any little anomalies or kind of blips in our graphs there. So we can look at different elements to compare them, or we can look at a single element and we can keep removing electrons one at a time and look at what patterns we get. So let's start with that one. Let's go over here for a minute. Now here I've graphed the ionization energies for chlorine as we successively or continually remove an electron. So down here, this is what would happen if we took chlorine as a gaseous atom and we were to turn it into this cation, which is quite unusual for chlorine. It's not the chloride ion we'd usually expect, but we are removing an electron and we are making it a positive ion here. So this is the energy required to do that. And we can see that over this part of the graph, that gets a little bit harder as we go. And really the most basic reason for that, if we compare what's happening there next, so this in blue, we have the first ionization energy. And we might put that as sort of an I with a little 1. And then we might have this second ionization energy here, and you go on, so on and so forth, third, fourth, fifth, etc. And so when we look at the second ionization energy, we're talking about the chlorine has already become slightly positive, and we're making it even more positive by removing another electron. So each time we move across this graph, we are taking away yet another electron from chlorine. And every time we do that, we are making it a more positively charged ion. So we are in a kind of tug of war between protons and electrons in the chlorine. We are really shifting the balance in favor of the protons because the electrons are moving away. So if we were to think about that as this kind of Bohr sort of model over here, this kind of planetary orbit model of the atom, that might help us think about sort of what's happening or core charge. So if you're not given that much thought or you can't remember, we would look at like chlorine, for example, its atomic number is 17, so it has 17 protons in the middle. Now these electrons here, these two in this sort of inner shell or principal energy level, and these ones is 8 over here, they are effectively blocking in a kind of 1-to-1 ratio. And this is just a model, it's simplified, but they're kind of blocking the effect or the attraction of that nucleus to the outer electrons. So what ends up being felt, if you like, or experienced by the valence electrons, we would subtract 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we would take 10 away from that. So we would say that the effective nuclear charge being reached by the valence shell is 7. And that's being shared, when we look at a chlorine atom, that's being shared by those 7 electrons that have to be pulled in. Now, if we remove one of those electrons, let's say we get rid of this one, we haven't changed that core charge. We've still got the same number of shielding electrons, so this hasn't actually done anything, it hasn't gone anywhere, but now that effective charge of +7 is being split by 6 electrons here. So each one is just feeling a little bit more, that attraction spread to those electrons. So they're pulled in a little bit tighter, held a little bit closer. We often also talk about ionic radius changing as a result of this. But it means that to then go and lose, sorry, that's being deleted. If we then go and try to lose another electron, it's that little bit harder and then yet another and another, and we can work our way around. So if we go back to our graph over here, we can lose those 7 valence electrons, and then what you might imagine, perhaps we need like another picture of that one, or to erase a few things here. Let me get rid of this highlighting. But if we get rid of all those valence electrons, we are now moving down to the shell below. And we start removing some of these ones. So the number of shielding electrons is only 2. Now only that inner shell is blocking the effective charge. It's reaching our new kind of valence shell, if you like. So we've actually now got only 2. So we really have a charge of 15 reaching that second shell, which is a lot stronger to hold those electrons there. So we can see quite a jump over here. And then even bigger again, if we keep taking electrons away, so we take all 7 in the valence shell and then all 8 in the second shell, look at the size of the jump then. The energy required to remove the innermost electrons is absolutely enormous. So if we keep taking electrons away from a single atom, we're talking about the same element and we're taking an electron away and then more and more and more, and we're making it more positive, it is of course going to get increasingly more difficult, and especially so when you make a jump from one shell to the next, one principal energy level. Now, when we look at exam questions or you have information like this, it's actually quite rare that you would look at a linear scale here. So if we were to look at this scale, I've just plotted that in even increments. That's what I mean by linear. What typically we look at to kind of stretch out this bottom part of the graph is to put it on a log scale. So if you've not seen anything like that before, have a look. This goes 1,000, 10,000, 100,000, a million. And look at these lines here, you know, that's 2,000, 3, 4, 5, 6, 7, 8, 9, and they get closer and closer together. So what it does is it stretches out this bottom part of the graph down here and condenses the top. So this is something to be mindful of when you're comparing these these jumps that are here and here, that actually this is the same information that's been displayed on our linear graph. It's exactly the same data, but it's just been dispersed differently on this logarithmic scale so that we can kind of focus on this zone down here and stretch that out and look for any differences. So overwhelmingly, our main trend that we have here with successive ionization energies is that we are making the ion more positive, so it is getting overwhelmingly more difficult to remove electrons as we go. And the big jumps from principal energy levels and from shells are because we lose a whole shell of shielding electrons every time. So let's maybe annotate that there. And shielding electrons, shielding the nucleus, which is where our positive charges are held, our protons. So that's happening there and there. So that's what happens with a single element. If you wanted to zoom on this a little bit more, you would see that it's not a perfect kind of trend. And if I put this ruler kind of here just to kind of exaggerate the gradient, we can see it's not a straight line. That actually, you know, our first couple, a bit harder to remove, and then actually we see the graph kind of flatten a little bit here. And these kind of little blips, if you like, these discontinuities. And we explain that, we can look at that if we want to go into a bit more detail, just due to the subshells. So the orbitals that make up the different sort of sub-levels within a principal energy level. And if we look at something like this, we can see like the electron configuration of chlorine, for example, 1s2, 2s2, 2p6, 3s2, 3p5 here gives us our 17 electrons in total. And when we remove an electron, So if I start to ionize this, it'll be this one here. Oh, sorry, that eraser was too large. took both away. That wasn't meant to happen. Maybe I can do that a little neater next time. So that's our first electron. That corresponds to, let's stick purple, that corresponds to this one. That was our easiest one to lose. And then we lose another one. That's the next one over here. And then we keep losing them. 1, 2, 3. Okay, and then what we can see here is this small kind of, you know, compared to that, like this angle changing here, I'm just trying to exaggerate that for you. This is because we've gone from the 3p to the 3s. The 3p is slightly higher in energy configuration 3s. So these 3s are held a little more tightly to the nucleus. So in order to pull them away, it's not the same as the big, you know, this difference here is not the same as going from the third shell down to the second. So the jump is not as significant as this one, but it is a little bit higher, that increase. So we can look for these small little discontinuities, and that gives us evidence for this model here of these orbitals, that actually not all third shell electrons are equal. So that's how we get some of that data. Overall, though, that main thing again, that successive ionization energies for a single element, the big thing is simply that it is becoming more positive, so it gets harder and harder to pull electrons away. If we look at different elements, here I've got a graph where I've got the first ionization energies. I've actually gone up to krypton, which is probably a little bit further than I need to go, but let's pop, you know, hydrogen, helium, lithium, beryllium, and so on. Maybe if I just shortcut that, you can see straight away the noble gases stick out. Or, you know, you might notice too, the group 1 metals, for example. So what have we got? We've got potassium down there. And we can notice that straight away that our noble gases here have very high first ionization energies. I should point out while I'm here actually, that when I say first ionization energies, if you don't have a working definition of that, make sure you jot this down in your notes. So ionization energy 1, that's what we mean by first ionization energy. I've gone the Z. I do tend to prefer British spelling, but this is in your course. First ionization energy, so that's the energy required to remove a mole of electrons from a mole of gaseous atoms in the ground state. So key things to note here, they're a gas, so there are no intermolecular forces or lattice enthalpies to overcome, that the energy that's input is going purely to removing electrons. And we want to be sure that the electrons are in the ground state, that they're not already electrically excited. So the electrons are in their kind of natural resting shells, if you like, the configuration we would expect to find them in. So here, we're not talking about successive things anymore. We're not going to keep ripping electrons away. We're going to turn all of these elements into +1 cations. That's our only job with first ionization energies. But we can see here it's incredibly difficult to do that to a noble gas. When you have full octets, when you have full orbitals, you have a lot of symmetry that gives a lot of electrical stability to our shells and our orbitals, and they have the highest effective nuclear charge holding their valence shell there. They are at the very end of the period, and so by definition they are the ones with the highest core charge. So they are holding their electrons there quite tightly. The opposite of that, of course, are our group 1 alkali metals. Let's pop them, pick another colour for them. So down here, these ones are easiest to ionize. So we can see that our trend overall, if we look at going across a period here, the overwhelming trend, or the kind of overarching thing here, is that core charge or effective nuclear charge. So the force that is experienced by the valence electrons from the protons in the nucleus, that has increased as we go along here. So as we move across the period in the periodic table, every time we add an extra valence electron, it doesn't add any shielding, but we do add an extra proton. So we increase the positive force that is felt by the valence electrons. So overall, it gets increasingly difficult to rip an electron away from these elements as we move across. But here we have some kind of more noticeable discontinuities, or the kind of blips, if you will. Here's a big one. Boron is lower than beryllium. That's boron there, by the way. And here, let me add a few other names in case you've lost track of the elements. Oxygen takes a dip down from nitrogen, and we look at this with our orbitals yet again, and it's more pronounced here. When we have a single element and the successive ionization energies, the effect of becoming a more positive ion outweighs the sort of orbital effect much more, so it's on a much greater scale. But here, they're all neutral atoms. So if we look at, let's sort of zoom out so we can see these. Okay, so hydrogen, helium, lithium, beryllium. There's beryllium, where we're trying to poach away an electron here. Compare that to boron over here. So we can see that the jump from this, and I haven't labeled these, I'm sorry, that's very bad of me, 2s to 2p, that was 1s down there, that the jump up to the subshell, if you're curious, by the way, or you're not clear about that, we call this one of these. This in itself is a single orbital. A collection of orbitals of all the same type that are degenerate are considered a subshell. And then the whole thing, that all are two, that's one shell or one principal energy level. So the fact that we've gone from one subshell to another, or one type of orbital to another, has meant that we have made a little jump here in energy. So this 2p orbital there, its probability of where the electrons are found, we can see that it's in this higher energy configuration, so not as tightly held by the nucleus, making it a little bit easier to pull away. That's our jump down from beryllium to boron. What's happening with nitrogen and oxygen? Okay, so let's get rid of that one there. So here we're going from boron, carbon, nitrogen. All of these here are half-filled orbitals. So each, there's a single electron occupying them. When we go from nitrogen to oxygen, we put another electron here in the same orbital. Now they do have opposite spins to reduce repulsion, but there's repulsion. There are two like charges, two electrons, they're pushing against each other. So that means that this electron here is in fact easier to remove. This electron here, that is accountable for this one. So I should try and go back to this diagram here, and it's a bit messy. I'm not the best at this. Let's pop a little explanation. S to P. So we've jumped up from an S orbital to a P orbital, and the P orbital is less tightly held. And this one is half filled P to full P over here, which means it's got electron repulsion. It's being pushed away by its partner in its orbital. So So that's what we see here. Now we can look at the trends, we can keep going down the periodic table if we want to, and we can see that overall the same trend is happening in period 3, that we have an increase in effective nuclear charge leads to an overall increase in the first ionization energy. And we can see again that we have, this is 2s1, 2s2, and then we go to 2p, and we have that drop, that dip. It is easier to remove from an electron from the p orbital than it is from the s. And then we go up, our p fills 1, 2, 3, they're all half filled. And then this one is completely full, so it's paired. So there is some electron-electron repulsion. And then we start moving back up again. And then we drop down. So the pattern continues. When you get down to here, I mean, you don't need to really worry, but we get some kind of strange things happening with our transition metals, or at least it gets a little bit more complicated, and the trend kind of flattens out, if you like, across here. Because actually what's happening with our transition metals is that most of them, not all of them, but most of them have 4s2 as their valence shell, because then they are filling 3d, all of those. And actually when we ionize, and remember we're only talking about first ionization energy, so just one electron, we take it from the valence shell. It's meant to highlight that one. So they're actually all relatively similar in here, because they sort of have the same degree of, like, the shielding, the 3d that's filling up. That shielding effect is kind of matching the increase in nuclear charge. So we see that kind of flattening out. You don't need to worry too much. You might be interested to sort of note things like, you know, chromium, for example, and copper that have the 4s1. And there are some other strange things that happen if you look a bit more into transition metals and what happens when they ionize. The 4s and the 3d, if we were down here, for example, I should put 3s, 3p, and that's 3d over here. And then 4p. So, okay, so we fill like this. And we do that strange thing with our chromium stealing that electron and then going back to what we'd expect. And then our copper doing the same thing, taking one from that s orbital because it's more electrically stable to have the symmetry of full degenerate orbitals where there are more than one. So taking that electron out of the 4s stabilizes the 3d. That's our copper over here, and then we go back to filling it up, and then we continue with our 4p until we have a completely full here at the end at krypton. But what you've got then, sort of looking at this trend, is that actually while this 3d orbital over here, what if that presses there? So my mouse is really bad. If that's actually progressively filling, every time we're filling kind of a shield, adding another shielding electron as we go across, and then this 4s is mostly staying the same. We just got these small little changes there with the copper, the chromium and the copper, but we've got quite sort of a much flatter trend in ionization energy, and then we sort of continue on as normal as you would expect for the section there up to krypton. Sorry, that's jumped all over the place. Okay, big things to summarize then. Make sure you are happy that with a single element, it becomes increasingly more positive, the ion, as we ionize it, so it gets harder to rip away electrons, and we see a big effect in dropping down from a principal energy level, also called a shell, because our number of shielding electrons drops when we do that, and we get a lot closer to the nucleus. We often see that data presented in logarithmic form to kind of stretch out those trends and patterns to have a look at both ends of the scale. And then when we compare different elements, we can see that the sort of main factor here going across a period is that the effective nuclear charge is increasing, and so its pull on those electrons is stronger and it makes it harder to remove them. But also we have evidence for our suborbitals, our subshells, because we can see these small little discontinuities that actually, as we jump from an s orbital to a p orbital, it gets easier to remove because the p is slightly more loosely held. And also, if the p orbitals have paired electrons or not, that affects their repulsion. So being paired with another electron means it's a little bit easier to remove in the case of oxygen compared with nitrogen. So that's what we see with those ones. The only other thing to point out too, and you can see it with the group 1 elements here, lithium, sodium, potassium. You can probably see it better. I sort of put that there. Hard to kind of line it up very well. Or you can see it certainly with the first 3 noble gases. Gets a little trickier after that. But we have a small trend downwards down a group. And that's simply because we're going to principal energy levels of shells that are further from the nucleus as well. So that's probably our other main trend to put on there. Is it down a group? First ionization energy decreases. And we'll just simplify that by saying due to more shells. Or distance from the nucleus. And I think that pretty much covers it. Hopefully that does for most people, and that's been helpful.